Right now, at this exact moment, try to imagine nothing. Not darkness, not emptiness, not a vast, black void stretching out in every direction. Because even that, even a void, even darkness, even emptiness, is still something. It is still space. It is still a place where things could exist but don't. What I'm asking you to imagine is far more radical than that. I'm asking you to imagine the absence of space itself, the absence of dimension, of direction, of distance. No up, no down, no left, no right. No here, no there. And it gets worse, because I'm also asking you to remove time from the picture. No before, no after, no duration, no flow, no ticking clock measuring the seconds that aren't passing, no seconds at all, no moments, no waiting, not even the possibility of waiting. You can feel the strain, can't you? That almost physical sensation of your mind pressing against a wall it cannot breach. That moment when your thoughts slip off the concept like water off glass. Because the human brain evolved to navigate a world of objects, of distances, of befores and after. It evolved to track the trajectory of a thrown spear, to remember where the ripe fruit grew last season, to predict the path of the sun across the sky. It was not built, not designed in any way, to contemplate the absence of sky itself, and yet that is exactly the question. The question that has haunted philosophers and priests and physicists for thousands of years. A question so fundamental, so staggeringly basic, that even framing it properly requires us to twist language into shapes it was never designed to hold. What came before the Big Bang? And here's what makes this question so maddening, so captivating, so utterly, beautifully unresolvable by common sense alone. If the Big Bang was the beginning of everything, if space, time, matter, and energy all erupted into existence roughly 13.8 billion years ago, then the word before shouldn't even apply. Asking what came before the Big Bang would be like, well, asking what's north of the North Pole. You can say the words. They feel like they should mean something. But when you actually try to point your compass in that direction, you find that the direction simply doesn't exist. And yet, physicists are asking this question, not just whispering it at dinner parties, not just musing about it philosophically over a glass of wine, but writing equations about it, building theories, making predictions. And some of those predictions are actually testable. Some of those predictions are being tested right now with satellites and telescopes and instruments sensitive enough to detect faint echoes of events that may have happened before the universe itself was born. Over the past 4 decades, a remarkable collection of ideas has emerged from the sharpest minds in theoretical physics. Ideas that propose our Big Bang was not the beginning of everything, but merely a transition, a phase change, a violent hiccup in a much larger, much older, perhaps even eternal cosmic story. Some of these theories suggest our universe bounced into existence from the collapse of a previous one. Others propose that it budded off from a vast, eternally inflating multiverse, like a bubble, forming in a pot of boiling water. Still, others imagine that our universe has a twin, a mirror image running backward through time, composed entirely of antimatter, existing on the other side of the Big Bang, like a reflection in a cosmic looking glass. And one particularly haunting idea, proposed by a Nobel Prize-winning physicist, suggests that the universe cycles through infinite ages, each one lasting trillions upon trillions of years, each one ending not with a bang, but with a slow, cold fade into a state so empty, so devoid of structure, that it becomes mathematically indistinguishable from the conditions of a new Big Bang. In this picture, the death of one universe is the birth of the next, and it has been happening forever. These are not fairy tales. These are not science fiction premises dressed up in academic language. These are serious theoretical frameworks built on the mathematics of general relativity and quantum mechanics, proposed by some of the most accomplished physicists alive today. And while none of them has been proven, and while the ultimate answer may lie beyond the reach of any experiment we can currently conceive, the mere fact that we can even begin to ask these questions, that we can push the boundaries of knowledge right up to the edge of time itself and peer over, well, that might be the most extraordinary thing our species has ever done. What makes this moment in the history of cosmology so special is that these are not idle speculations. Each of these theories makes specific predictions about things we can actually measure. Patterns in the cosmic microwave background, the spectrum of primordial gravitational waves, the mass of neutrinos, the distribution of galaxies on the largest scales, the properties of dark matter. These predictions are being tested right now with instruments of exquisite sensitivity pointed at the sky from mountaintops in Chile, from the frozen plains of the South Pole, and from satellites orbiting the Earth far above the atmosphere. The next decade or two of observations could well tell us which of these theories, if any, is correct. We may be the generation that finally answers the question of what came before the beginning. Or we may not. The universe is under no obligation to reveal its secrets on our timetable. But either way, the journey of inquiry is worth taking. So tonight, let's go there together. Let's walk right up to the edge of everything we know. Let's look backward past the first light, past the first atoms, past the first fractions of the first second, past even the moment of the Big Bang itself. Let's ask, as seriously and as honestly as we can, what was there before there was anything at all? Let's find out. For most of human history, the question of cosmic origins was answered by myth. Every civilization had its story. The ancient Egyptians imagined the world emerging from a primordial ocean of chaos called Nun. The Hindu tradition described the universe being dreamed into existence by the god Brahma, only to be destroyed and recreated in vast cosmic cycles lasting billions of years. The ancient Greeks debated endlessly about whether the cosmos was eternal or created. Aristotle argued for an eternal universe with no beginning, while the Stoics proposed a cyclical cosmos that was periodically consumed by fire and reborn. And then there were the Abrahamic traditions, with their deceptively simple opening line that has echoed through Western culture for millennia. In the beginning, God created the heavens and the earth. This formulation placed a definitive starting point on reality itself. The universe began. Something caused it to begin, and what came before was simply not a question that mortals were equipped to answer. But then something changed. In the early 20th century, human beings developed the mathematical and observational tools to actually investigate the origin of the cosmos empirically, and what they found was astonishing. In 1915, Albert Einstein published his general theory of relativity, a framework that described gravity not as a force pulling objects together, but as the curvature of spacetime itself, caused by the presence of mass and energy. The equations were beautiful, but brutally difficult to solve. And they contained a surprise that Einstein himself did not want to accept. His equations seemed to predict that the universe could not be static. It had to be either expanding or contracting. Einstein was so troubled by this implication that he famously introduced a fudge factor into his equations, a term he called the cosmological constant, specifically designed to keep the universe still. He would later call this the biggest blunder of his career. Because in 1927, a Belgian priest and physicist named Georges/Lemaitre/ took Einstein's equations seriously, worked through the mathematics, and proposed something extraordinary. He suggested that if the universe was expanding, then running the clock backward would mean it was once much smaller, much hotter, and much denser. Trace it all the way back, and you'd arrive at what /Lemaitre/ poetically called the primeval atom, a single, incomprehensibly dense point from which everything we see today emerged. 2 years later, the American astronomer Edwin Hubble provided the observational evidence that confirmed the expansion. By studying the light from distant galaxies, Hubble showed that they were all moving away from us, and that the farther away a galaxy was, the faster it was receding. The universe wasn't just expanding, it was expanding everywhere, in every direction, like the surface of a balloon being inflated. And so, the Big Bang theory was born, not with a single discovery, but with a slow accumulation of evidence that gradually forced the scientific community to accept a staggering conclusion. The universe had a beginning. Space itself was born. Time itself had a starting point. And everything we see around us, every star, every galaxy, every atom in your body, was once packed together into a state of almost unimaginable density and temperature. But what exactly was that state? What was the Big Bang, really? Well, here is where things get both fascinating and frustrating in equal measure. Because the Big Bang, despite its dramatic name, was not an explosion in the conventional sense. There was no pre-existing space for it to explode into. There was no moment of silence before the detonation. The Big Bang was the expansion of space itself, the stretching of the very fabric of reality from an extremely hot, extremely dense state into the gradually cooling, gradually thinning universe we inhabit today. And the evidence for this is overwhelming. The most powerful single piece of evidence is something called the cosmic microwave background, often abbreviated CMB, discovered accidentally in 1965 by 2 radio astronomers named Arno Penzias and Robert Wilson. The CMB is a faint glow of microwave radiation that fills every corner of the sky. It is, quite literally, the afterglow of the Big Bang. The light from the earliest moments of the universe, stretched by 13.8 billion years of cosmic expansion into long, cold microwave wavelengths. The story of its discovery is one of the great accidental triumphs in the history of science. Penzias and Wilson were working at Bell Labs in Holmdel, New Jersey, using a large horn-shaped antenna originally designed for satellite communication. They weren't looking for the echo of creation. They were trying to calibrate their instrument for a radio astronomy project, and they kept picking up a persistent, low-level hiss of microwave radiation that they couldn't account for. The signal was coming from everywhere. It was the same intensity regardless of which direction they pointed the antenna. It didn't vary with the time of day, the season, or the orientation of the Earth. It was always there, uniform, omnipresent, maddening. They checked everything. They tested the electronics. They rebuilt connectors. They even climbed into the horn of the antenna and scraped out a layer of pigeon droppings that had accumulated inside. Thinking the birds might be causing the signal, the pigeons were trapped, driven to a distant location, and released. They flew right back. The pigeons were removed again, more permanently this time. The signal persisted. Meanwhile, just 40 miles away at Princeton University, a team of physicists led by Robert Dicke had been building their own antenna specifically to search for this exact radiation. Dicke knew, from theoretical work done in the 1940s by George Gamow, Ralph Alpher, and Robert Herman, that if the Big Bang had actually happened, the universe should be filled with a faint glow of leftover radiation, cooled by billions of years of expansion to a temperature of just a few degrees above absolute zero. When Dicke heard about the mysterious signal that Penzias and Wilson couldn't get rid of, the story goes that he turned to his colleagues and said, "Boys, we've been scooped." 2 papers were published simultaneously in 1965, one from Penzias and Wilson describing the observation, one from Dicke's team explaining what it meant. The universe was bathed in radiation left over from a time when the entire cosmos was a searingly hot, opaque plasma, roughly 380,000 years after the Big Bang. Before that moment, the universe was so hot and dense that atoms couldn't form. Electrons were ripped free from atomic nuclei, creating a fog of charged particles that light couldn't penetrate. But at 380,000 years, the universe cooled enough for electrons to combine with protons and form neutral hydrogen atoms. Suddenly, the fog cleared. Light was free to travel, and it has been traveling ever since, in every direction, cooling and stretching as the universe expanded, until it became the faint microwave whisper that Penzias and Wilson stumbled upon in New Jersey. Since then, satellites like COBE, WMAP, and Planck have mapped the CMB with extraordinary detail, revealing tiny temperature fluctuations, variations of just 1 part in 100,000 that represent the seeds of all future structure in the universe. These subtle variations would eventually grow under the influence of gravity into galaxies and galaxy clusters, and the vast cosmic web that gives our universe its structure today. The COBE satellite, launched in 1989, made the first detection of these fluctuations, and its lead scientist, John Mather and George Smoot, would later share the Nobel Prize for the discovery. WMAP, launched in 2001, sharpened the picture dramatically. And Planck, the European Space Agency mission that operated from 2009 to 2013, delivered the most exquisite map yet. A portrait of the infant universe, rendered in such fine detail that it constrains cosmological models with stunning precision. And every measurement, every map, every data point from these missions confirms the broad picture. The universe was once extremely hot. It was once extremely small. and it has been expanding and cooling ever since. The Big Bang model also predicted something else. It predicted the relative abundances of the lightest elements in the universe. In the first few minutes after the Big Bang, when the universe was a seething cauldron of protons, neutrons, and photons, nuclear reactions fused some of these protons and neutrons into helium, along with trace amounts of deuterium and lithium. The Standard Model predicts that roughly 75% of the ordinary matter in the universe should be hydrogen, about 25% should be helium, and a tiny fraction should be deuterium and lithium. And when astronomers measure the actual abundances of these elements in the oldest, most pristine regions of the cosmos, the numbers match the predictions beautifully. This is called Big Bang nucleosynthesis, and it's one of the most powerful pieces of evidence for the hot Big Bang model. So the evidence is overwhelming. The expansion of the universe, the cosmic microwave background, the abundances of the light elements, three independent lines of evidence, all pointing to the same conclusion. The universe was once in an incredibly hot, incredibly dense state, and it has been expanding and cooling ever since. But here's the thing that gnaws at the edges of this beautiful, well-confirmed picture. The standard Big Bang model, as successful as it is, doesn't actually explain the Big Bang itself. It describes what happened after. It describes the expansion, the cooling, the formation of the first particles, the first atoms, the first stars. But when you try to rewind the clock all the way back to the very beginning, to time equals 0, the mathematics breaks down. At that moment, according to general relativity, the density of the universe becomes infinite. The temperature becomes infinite. The curvature of spacetime becomes infinite. Physicists call this a singularity, and it is not a place or a moment that our current theories can describe. It is a boundary, a wall, a point where the equations we rely on simply stop working. And so the Big Bang, in a very real sense, is not an explanation for the origin of the universe. It is the limit of our explanation. It is the point where our best theory of gravity, general relativity, throws up its hands and says, I can't tell you what happens here. This is what makes the question of before the Big Bang so tantalizing, because if the singularity isn't real, if it's just an artifact of using the wrong theory in extreme conditions, then perhaps the story doesn't end there. Perhaps the story extends backward. Perhaps the Big Bang wasn't the beginning at all. Let's sit with that idea for a moment, because it really is a profound shift in how we think about reality. For most of the 20th century, the question of what came before the Big Bang was considered scientifically meaningless. If time began with the Big Bang, then before the Big Bang is a logically incoherent concept. There is no before if there was no time in which before could exist. This was the position taken by many of the 20th century's greatest physicists, including, most famously, Stephen Hawking himself. The question itself has ancient roots, of course. In the 4th century, the philosopher and theologian Augustine of Hippo confronted it directly. Someone asked him what God was doing before he created the universe. Augustine's answer was sharp. Time itself, he argued, was part of God's creation. Asking what happened before creation was meaningless because there was no before. Time and the universe came into being together. The question, he said, was like asking what is north of the North Pole. a phrase that wouldn't be reused for another 16 years. Hawking liked to illustrate the point with that very same geographical analogy. Asking what happened before the Big Bang, he said, is like asking what's south of the South Pole. You can keep traveling south, 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 until you reach the pole itself. And then, there is no more south. The direction simply ceases to exist. South, in Hawking's analogy, is like time. You can trace it backward through the history of the universe, through the formation of galaxies, through the cooling of the primordial plasma, through the first microseconds of existence, and then you reach the Big Bang and the direction vanishes. There is no more before. And this wasn't just Hawking being clever with words. There was real mathematical substance behind this claim. In the late 1960s and early 1970s, Hawking, working with the brilliant mathematical physicist Roger Penrose, proved a series of theorems that seemed to demonstrate the inevitability of the singularity under very general conditions. They showed any universe described by general relativity that contains the kind of matter we observe must have a point in its past where density and curvature become infinite. The singularity, it seemed, was not a bug in the theory. It was a feature. The universe really did have an absolute beginning. The impact of these theorems was enormous. They gave mathematical teeth to the idea of a cosmic beginning, elevating it from philosophical speculation to physical prediction. Penrose presented the first version of the theorem in 1965, showing that the gravitational collapse of a massive object must inevitably lead to a singularity. Hawking, who was still a graduate student at the time, recognized that this logic could be applied in reverse. If the collapse of a star leads inevitably to a singularity inside a black hole, then the expansion of the universe, run backward, must also lead to a singularity at the Big Bang. Over the next several years, Hawking and Penrose refined their arguments, culminating in a joint paper in 1970 that laid down the definitive version of the singularity theorems. The conclusion seemed inescapable under the assumptions of general relativity. With matter that behaves the way matter is observed to behave, the universe must have begun in a singular state. But here's where the story takes a turn that even Hawking didn't fully anticipate, because the Penrose-Hawking singularity theorems, powerful as they were, relied on a crucial assumption. They assumed that general relativity, Einstein's theory of gravity, was the complete and correct description of the universe, all the way down to the smallest scales and the highest energies. And we know that it isn't. General relativity is a classical theory. It describes gravity beautifully at large scales, the orbits of planets, the bending of light around galaxies, the rippling of spacetime during black hole mergers. But at the tiniest scales, at the level of atoms and subatomic particles, the universe is governed by a very different set of rules: quantum mechanics. And quantum mechanics and general relativity, despite being the two most successful theories in the history of physics, are fundamentally incompatible with each other. They use different mathematics, different assumptions, different conceptual frameworks. And when you try to combine them, when you try to describe a situation where both quantum effects and gravitational effects are important, like the conditions at the Big Bang, the mathematics produces nonsensical results. Infinities crop up everywhere. Predictions become meaningless. This means that the singularity predicted by the Penrose-Hawking theorems is almost certainly not real. It is an artifact of applying general relativity in a regime where general relativity doesn't work. It's like using a map of a flat Earth to navigate near the poles. The map distorts the territory because it wasn't designed for that situation. And this realization, this understanding that the singularity is probably a breakdown of our theory rather than a real feature of the universe, is what cracked the door open. Because if the singularity isn't real, then the universe might not have an absolute beginning. The story might extend beyond the Big Bang. There might, in some meaningful sense, be a before. Now, to be clear, we don't have a complete theory of quantum gravity yet. We don't have a single, unified mathematical framework that seamlessly combines quantum mechanics and general relativity. That remains one of the great unsolved problems in physics, perhaps the greatest. But we do have several promising candidate theories, several different approaches to quantum gravity, and many of them make specific predictions about what happens at the moment of the Big Bang. And those predictions are startling. In some of these theories, the Big Bang is replaced by a big bounce, a moment where a previously contracting universe reaches a minimum size and then rebounds outward. In others, the Big Bang is the collision of higher dimensional objects called brains in a space we cannot directly perceive. In still others, the Big Bang is a quantum fluctuation, a hiccup in the void, a spontaneous tunneling event that created the universe from literally nothing. Each of these ideas has strengths and weaknesses. Each makes different predictions about the universe we should observe, and each offers a radically different answer to the question of what, if anything, came before. So let's explore them one by one, starting with the theory that in many ways started it all. The theory that transformed our understanding of the first fraction of a second of the universe's life. The theory of cosmic inflation. It was December of 1979, and a young postdoctoral researcher named Alan Guth was sitting alone in his cramped office at the Stanford Linear Accelerator Center, scribbling in a notebook. Guth was 32 years old. He'd been bouncing between temporary academic positions for years, moving from Princeton to Columbia, to Cornell, to Stanford, each time on short-term contracts with no guarantee of permanence. He was a particle physicist, not a cosmologist, and his career to that point had been, by his own admission, unremarkable. He was smart, sure, but in a field populated by geniuses, being merely smart wasn't enough to secure a faculty position. But on this particular December night, something happened that would change the course of physics. Guth had been working on a problem related to magnetic monopoles, hypothetical particles predicted by grand unified theories of particle physics. The problem was this: if the early universe was as hot as the Big Bang model predicted, then these monopoles should have been produced in enormous quantities. The universe should be swimming in them. And yet, no magnetic monopole had ever been detected. Not one. The universe seemed conspicuously free of them. While working through the mathematics, Guth stumbled onto a mechanism that could solve this puzzle, and as he followed the implications, he realized the mechanism solved far more than just the monopole problem. It solved problems in cosmology that had been nagging at physicists for decades. The first was called the flatness problem. Measurements of the universe's geometry showed that space was very nearly flat, meaning that the angles of a triangle drawn on the largest possible scale would add up to almost exactly 180 degrees. But the equations of the standard Big Bang model predicted that any tiny deviation from perfect flatness in the early universe would have been amplified enormously over 13.8 billion years of expansion. For the universe to be as flat as we observe it today, the density of the early universe had to be fine-tuned to an almost absurd degree of precision, to within 1 part in a billion billion. It was as if someone had balanced the universe on a knife's edge at the moment of creation, and it had stayed balanced ever since. The second was the horizon problem. The cosmic microwave background is remarkably uniform. The temperature is the same in every direction to within 1 part in 100,000. But here's the puzzle. Regions of the sky that are on opposite sides of our view, separated by vast distances, could never have been in causal contact with each other in the standard Big Bang model. There simply hadn't been enough time since the Big Bang for light or any other signal to travel between them. They had never talked to each other, and yet they were at the same temperature. It was as if 2 people on opposite sides of the Earth, who had never met, never communicated, never even known of each other's existence, had independently decided to set their thermostats to exactly the same setting, to a precision of 5 decimal places. Guth's insight was elegant and devastating in its simplicity. What if, he proposed, the universe had undergone a brief but incredibly violent period of expansion in the first tiny fractions of a second after its birth? What if, for something like roughly 10 to the minus 35 seconds, the universe had expanded exponentially, doubling in size again and again and again, growing by a factor of at least 10 to the 26th power in an unimaginably brief flash? This period, which Guth called cosmic inflation, would solve everything. The flatness problem solved. Just as the surface of a balloon appears flat when you inflate it to enormous size, so too would the geometry of the universe be driven toward perfect flatness by the exponential expansion of inflation. No matter what the curvature of space was before inflation, afterward it would be indistinguishable from flat. The horizon problem solved. Before inflation, the entire observable universe was contained within a region small enough for all parts of it to be in causal contact. They could exchange signals, reach thermal equilibrium, and settle into the same temperature. Then inflation took this tiny, uniform patch and stretched it to cosmic proportions, far beyond the observable universe. The reason the CMB is so uniform is that all the parts of it we can see were once packed together, talking to each other in a region smaller than an atom. The monopole problem solved. Inflation diluted any monopoles produced before or during the inflationary period to such an extreme degree that we would never expect to find even one in the entire observable universe. That night in 1979, Guth wrote in his notebook a phrase that has become legendary in the history of physics. At the top of the page, in excited, slightly messy handwriting, he scrawled the words, "spectacular realization." He then circled the phrase and drew a box around it for emphasis. And he was right. It was spectacular. When Guth gave his first seminar on inflation in January 1980, word spread like wildfire through the physics community. Here was an idea that solved multiple deep problems in cosmology simultaneously, required no exotic new physics beyond what was already being discussed in particle theory, and made clear, testable predictions. It was the kind of idea that comes along once in a generation. The mechanism behind inflation is, at its core, surprisingly simple. In Einstein's general relativity, gravity is not always attractive. If the universe is filled with a material that has a very high energy density but a negative pressure, a kind of tension pervading all of space, then gravity becomes repulsive. Instead of pulling things together, it pushes them apart. And in the very early universe, the conditions for exactly this kind of exotic material may have existed. Guth imagined that the early universe was filled with a quantum field in a special state called a false vacuum. This false vacuum had enormous energy, but it was unstable, like a ball balanced on top of a hill. The energy of this false vacuum acted as a gravitational repulsion, driving the exponential expansion. As the field rolled off the hill, or tunneled through a barrier to a lower energy state, the energy was released and converted into the familiar particles of ordinary matter and radiation. The false vacuum decayed, inflation ended, and the hot Big Bang began. The physics of inflation draws from both general relativity and quantum field theory. The negative pressure of the false vacuum creates a gravitational repulsion that drives exponential growth. The energy stored in the vacuum then transforms, through a process called reheating, into the particles that would go on to form atoms, stars, and galaxies. It is a breathtaking theoretical construction, connecting the physics of the very small quantum field theory with the physics of the very large general relativity in a single unified narrative of cosmic origins. But Guth's original model had a problem. The exponential expansion needed a way to end, a way for the universe to transition from its inflating state back to the normal, cooling, expanding state described by the standard Big Bang model. And in Guth's version, this transition, called graceful exit, didn't work properly. The universe would inflate forever in some regions and stop inflating in tiny, isolated bubbles that could never merge to produce the smooth universe we observe. This problem was solved independently by Andrei Linde in the Soviet Union and by Andreas Albrecht and Paul Steinhardt in the United States, who developed a version of inflation known as new inflation or slow roll inflation. In their model, the transition from the inflating state to the normal state happened smoothly and everywhere, producing exactly the kind of hot, uniform, expanding universe that the Big Bang model describes. And so inflation was established, not as a replacement for the Big Bang, but as a prologue to it. Inflation tells us what happened in the first fraction of a fraction of a fraction of a second. The Big Bang in the inflationary picture is not the absolute beginning of the universe. It is the moment when inflation ends, when the exotic energy driving the expansion converts into the ordinary matter and radiation that fills the cosmos, when the universe transitions from its brief, violent, exponential youth into the long, slow, cooling adulthood we observe today. But if inflation preceded the Big Bang, then what preceded inflation? What set it going? What were the initial conditions that allowed this extraordinary expansion to begin? And this is where inflation, for all its elegance, leads us right back to the question we started with, because inflation doesn't eliminate the mystery of the ultimate beginning. It just pushes it back a step. And as physicists began to probe this question, they discovered something that even Guth hadn't anticipated, something that would take the idea of before the Big Bang and stretch it to its most extreme, most mind-bending logical conclusion. In the early 1980s, shortly after Guth published his groundbreaking paper on inflation, 3 physicists working independently arrived at the same startling conclusion. Paul Steinhardt at the University of Pennsylvania, Alexander Vilenkin at Tufts University, and Andre Linde, who had recently emigrated from the Soviet Union to Stanford. Each of them realized that inflation, once it starts, may never completely stop. This was not the conclusion any of them had been looking for. Steinhardt had been working on his own version of inflation, the new inflation model that solved the graceful exit problem in Guth's original theory. He thought he was building a tidy, self-contained story of cosmic origins. Instead, his calculations revealed something far stranger. Vilenkin, meanwhile, had approached the problem from a more mathematical angle, applying the tools of quantum field theory to the inflationary scenario. And Linde, always the boldest and most iconoclastic of the 3, was pushing the boundaries of what inflation could mean in the most extreme conditions. All 3 of them, working in their own offices, on their own timelines, following their own chains of reasoning, converged on the same unsettling result. Inflation was not a brief, isolated episode in the early universe. It was an ongoing process, a cosmic factory that once switched on could never be switched off. The reason is quantum mechanics. During inflation, the energy field driving the expansion, called the inflaton field, is subject to tiny random fluctuations. These fluctuations are an unavoidable consequence of the Heisenberg uncertainty principle, the fundamental quantum mechanical rule that says you can never know the exact state of a system with perfect precision. Usually, these fluctuations are insignificant, too small to matter. But during inflation, the expansion is so rapid, so violent, that even tiny quantum fluctuations get stretched to enormous scales. And here's the key insight. In some regions of the inflating space, the quantum fluctuations push the inflaton field in a direction that makes inflation continue. In other regions, the fluctuations push it the other way, and inflation ends. Where inflation ends, you get a hot Big Bang, a universe like ours, expanding, cooling, forming galaxies and stars and planets, and eventually people who wonder where it all came from. But the regions where inflation continues keep inflating. And they inflate exponentially, so they quickly become much larger than the regions where inflation has ended. And within those still inflating regions, new quantum fluctuations create new pockets where inflation ends, producing new universes. And the remaining inflating regions keep inflating and producing more pockets. The process, once started, never stops. It goes on forever, an endless cascade of universes bubbling into existence within an eternally expanding background. This is called eternal inflation, and its implications are staggering. Andre Linde, who had independently developed his own version of inflation, called chaotic inflation, was one of the key figures in developing the idea of eternal inflation. Lind, a colorful and passionate physicist who had grown up in the Soviet Union and emigrated to the United States, realized that the self-reproducing nature of inflation was not a bug in the theory. It was a feature, and it transformed our understanding of what the universe actually is. Lind's chaotic inflation model proposed that inflation could begin from almost any initial conditions, as long as a small patch of space had sufficiently high energy. The inflatoned field didn't need to start in a special state or a particular configuration. It could start anywhere on its potential energy curve. If the energy was high enough, inflation would occur, and once inflation started, it would create conditions for more inflation, spawning an ever-growing fractal of inflating and non-inflating regions. Lind described the resulting picture as a self-reproducing inflationary universe. He imagined a vast, perhaps infinite, space in which inflation was the normal state of affairs, and universes like ours were tiny, isolated patches where inflation had locally ended. The creation of our universe in this picture was not a unique event. It was an ordinary process happening constantly, everywhere, throughout an infinite cosmic landscape. In the picture of eternal inflation, our universe, the one we can see with our telescopes, the one whose cosmic microwave background we've mapped with such exquisite precision, is just one bubble in an infinite, ever-growing cosmic foam. There are other bubbles, infinitely many of them. Each one is a universe unto itself, vast beyond comprehension, potentially containing its own galaxies, its own stars, its own planets, possibly even its own forms of life, and each bubble is completely isolated from every other bubble. The space between them is inflating so fast that no signal, not even light, could ever bridge the gap. We can never see them, never visit them, never communicate with them. They are, in every practical sense, separate realities. And here's where it gets really wild. String theory, the leading candidate for a theory that unifies gravity with the other fundamental forces, predicts a vast number of possible configurations for the fundamental constants of nature. The number is often estimated as something like 10 to the 500th power, a 1 followed by 500 zeros. This enormous collection of possibilities is called the string landscape, and in the framework of eternal inflation, each of these possible configurations can be realized in some pocket universe somewhere. Different universes can have different strengths of gravity, different masses for their particles, different numbers of spatial dimensions. The laws of physics themselves can vary from universe to universe. This is the multiverse, not as science fiction, but as a logical consequence of two well-motivated theoretical ideas: inflation and string theory. Now, let me be very clear about something. The multiverse is controversial, deeply controversial. Many physicists are uncomfortable with the idea, and for good reason. If other universes are fundamentally unobservable, then the multiverse hypothesis seems to defy the basic principle that scientific theories should make testable predictions. What good is a theory if you can never check it? But proponents argue that the multiverse is not something they chose to believe in. It's something their equations forced on them. Alan Guth himself has said that eternal inflation is a nearly inevitable consequence of the inflationary models that best fit our observations. If you accept inflation, and if you take quantum mechanics seriously, then the multiverse seems to follow whether you like it or not. And there are potential observational tests, at least in principle. If our universe is a bubble that nucleated within a larger inflating space, then it's possible that our bubble could have collided with neighboring bubbles early in its history. Such a collision would leave a distinctive signature in the cosmic microwave background, a circular pattern of temperature anomalies. Teams of physicists, led by researchers like Haranya Paris and Matthew Johnson, have actually searched for these signatures in the CMB data from the Planck satellite. So far, they haven't found convincing evidence. But the search continues, and future experiments may have the sensitivity to detect these faint echoes of bubble collisions, or to rule them out entirely. But the multiverse raises another, even more fundamental question. If inflation is eternal into the future, is it also eternal into the past? Could the inflationary process have been going on forever, with no beginning at all? This is where a famous theorem, proved in 2003 by Arvind Borde, Alan Guth, and Alexander Vilenkin, becomes crucial. The Borde-Guth-Vilenkin theorem, often called the BGV theorem, shows that any universe that has been expanding on average over its history cannot be past eternal. It must have had a beginning. This doesn't tell us what that beginning was. It doesn't tell us what preceded it. But it does tell us that even in the framework of eternal inflation, the multiverse as a whole cannot extend infinitely far into the past. There must have been some kind of starting point. And that's, well, deeply provocative, because it means the question of origins hasn't been resolved by eternal inflation. It has, in some ways, been made more acute. Now, we're not just asking what happened before the Big Bang of our particular universe. We're asking what happened before the entire multiverse began. What ignited the process of eternal inflation in the first place? Some physicists, including Vilenkin himself, have proposed an answer. And that answer is nothing. Literally nothing. The universe, Vilenkin argues, tunneled into existence from a state of absolute nothingness through a process of quantum tunneling. In this picture, there was no time before the universe. There was no space before the universe. There was simply a probability, a quantum mechanical probability of something appearing where nothing had been. And that probability, however small, was realized. We'll return to this extraordinary idea shortly. But first, let's explore a very different approach to the question of what came before the Big Bang, an approach that doesn't invoke exotic quantum fields or infinite multiverses, but instead looks at the very nature of space and time at the most fundamental level, an approach that replaces the Big Bang not with a beginning, but with a bounce. There is a problem with the singularity at the center of the Big Bang, and it's the same problem that haunts the singularity at the center of a black hole. At these points, general relativity predicts infinite density and infinite curvature. But infinite is not a number that appears in nature. Whenever a physical theory predicts infinity, it's usually a sign that the theory has been pushed beyond its limits, that some crucial piece of physics is missing. And the missing piece, most physicists believe, is quantum gravity. We know that general relativity describes gravity beautifully at large scales. We know that quantum mechanics describes the behavior of particles and fields beautifully at small scales. But when you try to apply general relativity at very small scales, at distances comparable to the Planck length, roughly 10 to the minus 35 meters, you enter a realm where quantum effects should dominate gravity, and our current theories simply cannot handle that combination. Several different approaches to quantum gravity have been proposed over the decades. String theory is perhaps the most famous, but there's another approach, less well known to the general public, but deeply respected among physicists, called loop quantum gravity. And it has something very specific and very dramatic to say about the Big Bang. Loop quantum gravity, often abbreviated LQG, was developed primarily by Abhay Ashtekar, Carlo Rovelli, and Lee Smolin. Beginning in the mid-1980s, the central idea of LQG is that space itself is not smooth and continuous, as Einstein assumed, but is instead made up of tiny, discrete chunks. At the very smallest scales, space has a granular structure, like a fabric woven from incredibly fine threads. These threads, called spin networks, form the fundamental building blocks of geometry itself. Just as matter is made of atoms, space, in loop quantum gravity, is made of tiny quantized units. Think about it this way. When you look at a sheet of cotton fabric from a distance, it appears smooth and continuous. You can drape it, fold it, stretch it, and it behaves like a uniform surface. But get close enough, look through a magnifying glass, and the illusion dissolves. You see individual threads crossing and weaving over one another with tiny gaps between them. The smoothness was always an approximation. Loop quantum gravity proposes that space itself works the same way. At the scale of everyday life, at the scale of planets and stars and galaxies, space appears perfectly smooth and continuous, and Einstein's equations describe it beautifully. But zoom in far enough, down to distances of about 10 to the minus 35 meters, the so-called Planck length, and the smoothness gives way to a granular, foam-like structure. The Planck length is almost incomprehensibly small. To give you a sense of scale, imagine an atom. An atom is already tiny, far too small to see with the naked eye or even a standard microscope. But the Planck length is to an atom as an atom is to the observable universe. That is how deep into the fabric of reality loop quantum gravity reaches. The spin networks that make up space in LQG are not static structures. They evolve over time, changing their shape and connectivity in response to the quantum fluctuations that govern their behavior. When you watch these spin networks evolve, you get what physicists call a spin foam, a four-dimensional structure that represents not just space, but spacetime itself, built from fundamental quantum pieces. It is a radically different picture of reality than the one Einstein gave us. And yet, at large scales, it reproduces all of Einstein's predictions exactly. The two descriptions converge, just as the view of individual threads converges into the appearance of smooth fabric when you step back far enough. And when you apply the principles of loop quantum gravity to the early universe, something remarkable happens. In the standard Big Bang picture, as you rewind time and the universe contracts, the density increases without limit, eventually reaching infinity at the singularity. But in loop quantum cosmology, the symmetry-reduced version of LQG applied to cosmological models, there is a limit. The granular structure of space creates a kind of resistance, a quantum repulsive force that becomes significant only at extremely high densities, close to the Planck scale. This force has no counterpart in classical physics. It doesn't exist in Einstein's equations. It is purely a quantum effect, arising from the discrete nature of spacetime itself, and this quantum force prevents the singularity from forming. As the universe contracts and approaches Planck scale density, the repulsive force grows stronger and stronger, overwhelming the attractive force of gravity. The contraction slows, stops, and reverses. The universe bounces. This is the Big Bounce. In the Big Bounce scenario, our Big Bang was not the beginning of time. It was a transition point, a moment of maximum compression, where a previously contracting universe reversed course and began expanding. Before our Big Bang, there was another universe contracting toward this bounce point. And before that contracting phase, perhaps there was another expansion. And before that, another contraction, and so on, possibly forever. Try to picture what the bounce itself would be like if you could somehow be present for it. The universe around you is contracting. Galaxies are rushing toward you from every direction. The sky is getting brighter as the cosmic microwave background, now a bath of increasingly energetic radiation, shifts from microwaves to infrared to visible light, to ultraviolet to X-rays to gamma rays. Space itself is compressing, squeezing matter and energy into an ever denser, ever hotter state. The temperature climbs past billions of degrees, past trillions, past the point where atoms dissolve into their constituent quarks and gluons. The density approaches the Planck scale, roughly 10 to the 93rd grams per cubic centimeter, a number so large that it makes the density of a neutron star look like a wisp of fog by comparison. And then the quantum pressure kicks in. The contraction slows, pauses, and reverses. The universe bounces, and what was a contraction becomes an expansion. The temperature begins to drop. Matter begins to cool, and a new cosmic history begins. A new Big Bang erupting not from a singularity, but from the maximum compression of a previous universe. The idea of a bouncing universe isn't new. Variants of it were proposed as far back as the 1930s by cosmologists like Richard Tolman. Tolman imagined a universe that cycled endlessly, expanding, contracting, bouncing, expanding again, like a cosmic heartbeat. It was an appealing picture, an eternal cosmos with no need for a beginning or an end. Albert Einstein himself was intrigued by the idea. He and Tolman discussed it at length during their time together at Caltech in the early 1930s, but those early bounce models were plagued by problems. The most serious was entropy. The second law of thermodynamics demands that entropy, the measure of disorder in a system, always increases. In a cyclic universe, each cycle should have more entropy than the last, which means each cycle should be different from the ones before it. Each successive expansion should be larger and longer than the previous one, and running this backward in time, the earliest cycles should have had incredibly low entropy, which raises the question of why. You haven't actually solved the problem of initial conditions. You've just moved it, but loop quantum cosmology offers a different perspective. In the simplest models, the bounce is a one-time event, not part of a repeating cycle. There was a previous universe that collapsed. It bounced once at the Planck density, and our universe emerged from the bounce. The question of what set the previous universe in motion remains. But the singularity, the infinity, the point where physics breaks down, that's gone. And with it goes the argument that time must have had an absolute beginning. Martin Bojhold, a physicist who did pioneering work on loop quantum cosmology in the early 2000s, showed that some properties of the universe before the bounce could, at least in principle, be determined from observations of the universe after the bounce. The quantum fluctuations that seeded the formation of galaxies in our universe could carry imprints of the pre-bounce epoch. The spectrum of these fluctuations, the pattern of how their intensity varies with wavelength, could be subtly different in a bouncing cosmology compared to a universe that simply began with a Big Bang. And this is where the rubber meets the road. Because the cosmic microwave background provides an extraordinarily detailed record of these primordial fluctuations. If the big bounce is real, its signature might be hiding in the CMB data, waiting to be found. Several groups of physicists have worked out what these signatures should look like, and they've compared their predictions with the data from the Planck satellite. So far, the results are tantalizing but inconclusive. Some features of the CMB that are slightly puzzling in the standard inflationary picture, like a lower than expected amount of fluctuation power at the largest scales, could potentially be explained by a pre-bounce epoch, but the evidence is far from definitive. The honest truth is that loop quantum cosmology is still a young field, and there are significant open questions. The biggest is the relationship between loop quantum cosmology, which works with simplified, symmetry-reduced models, and the full theory of loop quantum gravity, which is far more complex and not yet fully developed. It's possible that the bounce is an artifact of the simplification, that when you include all the messy details of the full theory, the bounce goes away. Or it's possible that the bounce is robust, that it survives the transition to the full theory and represents a genuine prediction of quantum gravity. We don't know yet, but the idea is beautiful, and it's testable, and it offers a vision of cosmic history that stretches beyond the Big Bang into an era that we might, one day, be able to explore. While some physicists were trying to eliminate the Big Bang singularity by quantizing gravity, others took a completely different approach. Instead of fixing the singularity, they proposed to dissolve it, to show that the Big Bang was never really a singular beginning at all, but rather a smooth, finite, self-contained origin that required no before. The most famous version of this idea was proposed in 1983 by James Hartle and Stephen Hawking. It is called the no-boundary proposal, and it is, without exaggeration, one of the most audacious ideas in the history of physics. To understand the no-boundary proposal, you first have to understand something about the relationship between time and imaginary numbers. This is going to sound strange. Bear with me. In ordinary physics, time is measured by real numbers. You can say the event happened at time t equals 5 seconds, and everyone knows what you mean. But in quantum mechanics, it's sometimes useful to perform a mathematical trick called a Wick rotation, in which you replace the real-time variable with an imaginary time variable. Now, imaginary here doesn't mean fake or made up. It means involving the square root of the negative one, the number that mathematicians call I, imaginary time, is a perfectly legitimate mathematical concept, and it turns out to be extraordinarily useful in quantum calculations. When you make this substitution, something remarkable happens to the equations of general relativity. In real time, there's a clear distinction between time and space. Time flows in one direction, space extends in 3 directions, but in an imaginary time, this distinction vanishes. Time becomes just another dimension of space. Instead of a 4-dimensional spacetime with 3 spatial dimensions and 1 time dimension, you get a 4-dimensional space with 4 spatial dimensions. And in this 4-dimensional space, the Big Bang singularity disappears. Hartle and Hawking proposed that the universe, when described in imaginary time, has no boundary, no edge, no singularity, no beginning. The universe, in their picture, is like the surface of a sphere. It is finite in extent, but has no boundary, no edge, no starting point. You can wander over every inch of a sphere's surface without ever encountering a wall or a cliff. Similarly, in the Hartle-Hawking model, you can trace the history of the universe all the way back without ever encountering a singularity. In imaginary time, the universe has the shape of something like a bowl or a hemisphere. The south pole of this hemisphere corresponds to the earliest moment of the universe's history, the point where, in ordinary time, we would say the Big Bang occurred. But in imaginary time, this point is no more special than any other point on the sphere. There's no edge there, no boundary, no discontinuity. The universe simply rounds off. It closes in on itself, smoothly and gently, like the bottom of a bowl. And when you translate this back into real time, you get a universe that appears to emerge from nothing. Not from a singularity, not from a point of infinite density, but from a smooth, finite quantum state. The universe has a beginning in real time, but that beginning is not a boundary. It's more like the way the surface of the Earth has a southernmost point without having an edge at the South Pole. Hawking described this with characteristic flair. The universe, he said, would be completely self-contained and would not be affected by anything outside itself. It would neither be created nor destroyed. It would just be. Now, the no-boundary proposal is beautiful, but it has faced significant criticism over the years. Some physicists have argued that when you actually do the mathematical calculations rigorously, the no-boundary wave function doesn't predict the kind of universe we observe. In particular, it seems to favor universes that undergo very little inflation, which contradicts our observations. This is a serious problem, and it's one that Hawking and his collaborators, including Thomas Hertog, spent years trying to resolve before Hawking's death in 2018. In fact, Hertog was one of Hawking's closest collaborators in his final years, and together they developed a refined version of the no-boundary proposal that attempted to account for the observational evidence. Hawking's last paper, submitted just weeks before his death in March 2018, and published posthumously, co-authored with Hertog, proposed a way to constrain the no-boundary proposal using something called holographic duality, a concept borrowed from string theory. In this paper, Hawking and Hertog argued that the no-boundary condition, when properly applied, didn't predict an infinite multiverse with wildly varying laws of physics. Instead, it predicted a universe that was relatively smooth and simple, with a limited range of possible outcomes. The eternal inflation that seemed to follow from other theories was, in their version, tamed. The multiverse, if it existed at all, was much more modest than the infinite landscape of possibilities that other physicists had imagined. It was a fitting final contribution from a physicist who had spent his entire career grappling with the deepest questions about the nature of reality. Hawking once said that his goal was to understand the mind of God, not in a religious sense, but in the sense of understanding the fundamental principles that govern the universe. The no-boundary proposal was perhaps his most ambitious attempt at that goal, an effort to show that the universe could explain itself, that it didn't need an external cause or a boundary or a moment of creation. It would just be around the same time that Hartle and Hawking were developing their no-boundary proposal. Alexander Vilenkin at Tufts University proposed a related but distinct idea. Vilenkin imagined the universe as a quantum particle that tunneled into existence from literally nothing. In ordinary quantum mechanics, particles can tunnel through barriers that they classically shouldn't be able to cross. A particle trapped in a well can spontaneously appear outside the well, even though it never had enough energy to climb over the walls. Vilenkin proposed that the universe itself could tunnel into existence in a similar way, appearing from a state with no space, no time, no matter, and no energy. To appreciate just how radical this idea is, it helps to understand what quantum tunneling actually looks like. In the quantum world, a particle doesn't have a definite position until it's measured. Instead, it exists as a probability wave, a fuzzy cloud of potential locations. When that probability wave encounters a barrier, a region of high energy that the particle shouldn't classically be able to cross, a small portion of the wave leaks through to the other side. There is a non-zero probability that the particle will simply appear on the far side of the barrier without ever having had the energy to cross it. This isn't science fiction. It's observed routinely in laboratories around the world. It's the principle behind the scanning tunneling microscope. It's the mechanism that allows nuclear fusion to occur in the cores of stars at temperatures lower than classical physics would require. Vilenkin took this well-established quantum phenomenon and scaled it up to the most extreme case imaginable. Instead of a single particle tunneling through a potential barrier, the entire universe tunneled from a state of non-existence into existence. In Vilenkin's model, nothing really means nothing. Not empty space, not a quantum vacuum. Nothing. And the universe appears from this nothing through a quantum tunneling event, emerging as a tiny, inflating sphere that rapidly grows to cosmic proportions. The laws of physics, the quantum mechanical rules that govern tunneling, are all that's needed. No cause, no creator, no precondition, just the mathematics of quantum gravity operating on the absence of everything. This idea is, deeply disorienting. It raises philosophical questions that physics alone may not be able to answer. Can something really come from nothing? What does nothing even mean in a quantum mechanical context? Is the nothing that Vilenkin describes truly nothing? Or is it simply a different kind of something? A state governed by quantum mechanical rules that themselves have some kind of existence. And if the laws of physics are needed to explain the tunneling, doesn't that mean the laws themselves existed before the universe? And if so, where did they come from? Vilenkin himself has grappled with these questions. He's written extensively about what he means by nothing, distinguishing carefully between the nothing of empty space, which is still a something because space itself has structure and energy, and the more radical nothing that his tunneling model invokes, which is the absence of space, time, matter, and energy altogether. The only thing that exists in Vilenkin's nothing is the laws of quantum mechanics themselves, or perhaps, more precisely, the mathematical structure that gives rise to those laws. It's a minimalist starting point, as close to genuine nothingness as you can get while still having a framework that allows you to do calculations. The philosopher David Albert has famously objected to this, arguing that a state governed by quantum mechanical laws is emphatically not nothing. True nothing, Albert insists, would have no laws, no structure, no mathematics, no anything at all. And from true nothing, nothing could ever emerge. The debate is, at bottom, a debate about what nothing means, and it remains unresolved. These are questions that take us to the very boundary between physics and philosophy, between science and metaphysics, and perhaps, for now, it's enough to note that both the no-boundary proposal and the tunneling proposal represent serious, mathematically rigorous attempts to describe the origin of the universe without invoking a singularity or an external cause. They don't answer every question, but they push the boundary of what we can say scientifically about the ultimate, beginning further than anyone thought possible. While Guth, Lind, and Vilenkin were developing inflation and its mind-bending consequences in the West, and while Hartle and Hawking were reimagining the geometry of time itself, a very different approach to the question of cosmic origins was taking shape in the mind of a British mathematician who would go on to win a Nobel Prize for his work on black holes. Roger Penrose was not like other physicists, where most theoretical physicists communicated through equations and computer simulations. Penrose thought in pictures. He was a visual thinker of extraordinary power, famous for his hand-drawn diagrams and his ability to see geometric relationships that others missed entirely. His conformal diagrams, now called Penrose diagrams, allowed physicists to represent the entire infinite expanse of spacetime on a single, finite sheet of paper, a tool that revolutionized the study of black holes and cosmology. He was also a man of wide-ranging interests, deeply engaged with the philosophy of consciousness, the nature of mathematical truth, and the limitations of artificial intelligence. His book, The Emperor's New Mind, published in 1989, argued that the human mind was fundamentally different from any computer, a claim that remains hotly debated to this day. But in the 2000s and 2010s, Penrose increasingly turned his formidable visual imagination to a problem that had bothered him for decades. A problem that he believed inflation had utterly failed to address. The problem was entropy. Roger Penrose had always been deeply troubled by the Big Bang, not by the singularity itself. He'd helped prove it existed, after all. What bothered Penrose was something subtler, something that inflation was supposed to explain, but in his view, utterly failed to. The second law of thermodynamics states that entropy, the measure of disorder in a system, always increases over time. A hot cup of coffee cools down. A neat arrangement of molecules becomes messy. An egg, once scrambled, stays scrambled. The universe, taken as a whole, is becoming more disordered with every passing moment. But here's the puzzle. If entropy always increases, then the entropy of the universe must have been lower in the past than it is today. And the further back you go, the lower the entropy must have been. At the moment of the Big Bang, the entropy of the universe must have been extraordinarily, almost inconceivably low. Penrose calculated just how improbable this low entropy beginning was. The number he arrived at is so staggeringly large that it defies any normal means of expression. It was 1 part in 10 to the power of 10 to the power of 123. That's not 10 to the 123rd. It's 10 to the 10 to the 123rd. A number with more digits than there are particles in the observable universe. Far more. The likelihood of the universe starting in the specific, highly ordered state that it apparently did is so vanishingly small that Penrose compared it to a creator, aiming a pin at a target so tiny that no conceivable analogy could capture its improbability. And inflation, Penrose argued, did nothing to solve this problem. Inflation could explain why the universe is flat and smooth, but it couldn't explain why the initial conditions that led to inflation were themselves so special. You still needed a staggeringly improbable starting state. The mystery had just been moved, not resolved. Penrose's solution was radical. He called it conformal cyclic cosmology, or CCC. To understand CCC, you first need to appreciate one of the strangest and most counterintuitive features of gravity: the relationship between gravitational clumping and entropy. In everyday life, entropy is associated with things spreading out, mixing, becoming disordered. Drop a bottle of ink into a bowl of water, and the ink disperses, spreading evenly throughout the water. The entropy has increased. To reverse this process, to gather the ink back into a single concentrated drop, would require a staggering decrease in entropy, something the second law says effectively never happens. But gravity is different. With gravity, clumping is the high entropy state, not the low entropy state. A smooth, uniform distribution of matter is gravitationally ordered. It has low entropy. When gravity pulls matter together into stars, galaxies, and eventually black holes, the entropy of the gravitational field increases enormously. Black holes, in fact, are the highest entropy objects in the universe. The entropy of a black hole is proportional to the area of its event horizon. And for a supermassive black hole at the center of a galaxy, this entropy dwarfs the entropy of all the stars and gas and radiation in the surrounding galaxy combined. This is the key to Penrose's argument. The early universe was smooth and uniform. Gravitationally, it was an extraordinarily ordered, low entropy state. Inflation can explain how the universe became so smooth and flat, but it can't explain why the gravitational degrees of freedom were so ordered. The gravitational field could have been wildly lumpy and chaotic at the Big Bang, and inflation wouldn't have smoothed it out. The low gravitational entropy of the early universe is a separate mystery, one that inflation doesn't address. The core idea of CCC is that the universe goes through an infinite sequence of eons. each of which begins with a Big Bang and ends with an infinitely extended, cold, empty future. In our current eon, the universe is expanding. Galaxies are moving apart, stars are burning out, and eventually, trillions of years from now, the cosmos will be a vast, cold, nearly empty void, populated only by photons and gravitons drifting through an unimaginably dilute space. But before the universe reaches that final state, something important happens. The black holes, those engines of maximum entropy, slowly evaporate. Hawking showed in the 1970s that black holes are not truly permanent. They radiate energy extremely slowly through a quantum process that bears his name, Hawking radiation. A black hole the mass of our sun would take roughly 10 to the 67th years to evaporate, an incomprehensibly long time. A supermassive black hole at the center of a galaxy would take perhaps 10 to the 100th years. These timescales are so vast that they make the current age of the universe, 13.8 billion years, look like the blink of an eye. But eventually, given enough time, every black hole in the universe will evaporate. And with them goes the enormous gravitational entropy they carried. The universe, in its ultra-far future, becomes dominated by massless radiation, photons and gravitons, drifting through an essentially empty space. Here's the clever bit. Penrose noticed something remarkable about the mathematical description of this far future state. In the very distant future, when all massive particles have decayed and only massless particles remain, the universe loses track of scale. When everything in the universe travels at the speed of light, as massless particles do, the concept of size becomes meaningless. There's no ruler to measure distance, because rulers require massive particles, and there aren't any. There's no clock to measure time, because clocks require massive particles too. The universe, in its dying moments, becomes conformally equivalent to a small, hot, dense state, and a small, hot, dense state is exactly what the universe looks like at the beginning of a new Big Bang. Penrose proposed that the infinitely stretched out future of one eon could be smoothly joined to the Big Bang of the next eon through a mathematical operation called a conformal rescaling. This is a transformation that preserves angles and shapes, but not sizes. The endlessly vast, cold future of one universe would be, from the perspective of conformal geometry, identical to the tiny, hot beginning of the next. In Penrose's picture, the Big Bang of our universe was not the absolute beginning. It was the crossover from the previous eon. Information, energy, and structure from that previous eon could leak through the crossover surface and leave detectable imprints in our universe. Specifically, Penrose predicted that the evaporation of supermassive black holes in the previous eon, through Hawking radiation, would leave distinctive hot spots in our cosmic microwave background. He called these Hawking points. In 2010, Penrose, working with the Armenian physicist Vah Gurzadian, published a paper claiming to have found evidence for these signatures in the CMB data from the WMAP satellite. They reported an excess of concentric circles of near uniform temperature that they argued was inconsistent with the standard inflationary model, but entirely consistent with CCC. The paper generated enormous excitement and enormous controversy. Several independent analyses argued that the circles Penrose and Gersonian found were actually consistent with the standard inflationary model once proper statistical methods were applied. The debate is ongoing, and most cosmologists remain skeptical. But Penrose has continued to publish new analyses, claiming increasingly strong evidence for Hawking points in the Planck satellite data. Whether CCC will ultimately be confirmed or refuted remains an open question. The theory makes specific, testable predictions, which is exactly what you want from a scientific theory, and even its critics acknowledge that it's a creative and mathematically sophisticated attempt to address one of cosmology's deepest puzzles: the entropy problem, the question of why the universe began in such a special state, is real, and Penrose's answer, that it didn't begin at all, but was instead the continuation of a previous eon's death, is, at the very least, profoundly thought-provoking. On a winter evening in 1999, two physicists found themselves sitting next to each other on a train from Cambridge to London. They had just attended a lecture by Bert Avrat on a topic from theoretical physics called heterotic M-theory. The lecture described a picture of the universe in which our three-dimensional world is a membrane, a brain, floating in a higher dimensional space called the bulk. And according to this picture, there wasn't just one brain. There were two parallel universes floating like sheets of paper in a higher dimensional room, separated by a tiny gap. The two physicists on that train were Paul Steinhardt and Neil Tirach. And as the English countryside slid past the windows, they turned to each other and asked the same question. What if these two brains collided? The idea that crystallized during that train ride would become one of the most ambitious alternatives to inflation ever proposed. Steinhardt and Tirach, along with collaborators Justin Cowery and Bert Avrat, published their theory in 2000, and one under the name the ekpyrotic universe. The name came from the ancient Greek word ekpyrosis, meaning conflagration, a term the Stoic philosophers used to describe their belief that the universe was periodically consumed by fire and reborn from its ashes. The central idea of the ekpyrotic model is this: imagine two parallel brains, separated by a small distance in an extra dimension that we cannot directly perceive. Gravity can propagate through this extra dimension, but all other forces, electromagnetism, the strong force, the weak force, are confined to the brains themselves. Our universe, with all its galaxies and stars and planets, lives on one of these brains. Try to picture it. Not easy, because we're talking about an extra spatial dimension beyond the three we can perceive. But imagine, as a crude analogy, two vast sheets of paper hanging parallel to each other in a room. Each sheet is a separate universe, a three-dimensional world unto itself. The inhabitants of each sheet, if there were any, would experience their world as complete and self-contained. They could move freely along the surface of their sheet, but would be utterly unaware of the gap between them, unable to reach out and touch the other sheet, unable to even detect its existence. The only thing that can cross the gap is gravity. It leaks between the sheets, providing a faint, almost imperceptible connection between two otherwise separate realities. Now, there is a force of attraction between the two brains. Slowly, imperceptibly, they drift toward each other. As they approach, the attractive force between them grows and the brains accelerate. You can imagine it like two enormous plates, each carrying an entire universe on its surface, sliding closer and closer together across a higher dimensional gap. The gap narrows, the approach quickens, and then, after an immense span of time that might, in some versions of the model, stretch across trillions of years, they collide. And this collision, this is the Big Bang. The energy released in the brain collision heats the matter on our brain, flooding it with the super-hot plasma that we identify as the early universe. Think of it like clapping two cymbals together. The collision converts the kinetic energy of the brain's approach into thermal energy, heat, radiation, particles, the whole searing contents of the early cosmos. The collision also creates the tiny ripples in density that seed the formation of galaxies. And crucially, the collision is not a point event. It happens everywhere across the brain simultaneously, or nearly so. The slight variations in timing, caused by quantum fluctuations that wrinkle the brains as they approach, produce the nearly scale-invariant spectrum of density perturbations that we observe in the CMB. After the collision, the brains bounce apart, and the universe enters its normal, decelerating expansion phase. Galaxies form, stars ignite, planets coalesce, life emerges, and then, after many billions of years, the mysterious dark energy that currently drives the acceleration of the universe's expansion is reinterpreted, in this model, as the very slight attractive force between the brains. Eventually, this force draws them together again. The brains approach. They collide. Another Big Bang. The cycle repeats. This is the cyclic model of the universe, and it has some remarkable features. Imagine cosmic history not as a single arc from birth to death, but as a rhythm. An endless oscillation like breathing. Expansion, contraction, collision, expansion. The universe inhales and exhales over and over again, each breath lasting perhaps 1 trillion years. Each collision floods the universe with fresh energy, fresh particles, fresh opportunities for the formation of galaxies and stars and planets. And between each breath, the universe expands, cools, evolves, and eventually, the dark energy that currently accelerates its expansion is reinterpreted as the subtle pull of the second brain, drawing the two sheets back together for another collision, another cosmic renewal. First, it explains everything that inflation explains: the flatness, the homogeneity, the density perturbations, but through completely different physics. Instead of a brief period of exponential expansion, the ekpyrotic model uses a long period of very slow contraction before the bounce. During this contraction phase, the brains become extremely smooth and flat, naturally producing the uniform initial conditions that are otherwise so puzzling. Second, the cyclic model avoids the multiverse. In inflation, quantum fluctuations inevitably lead to eternal inflation and the proliferation of infinitely many pocket universes with different physical properties. In the ekpyrotic model, the smoothing happens during contraction, and quantum fluctuations are not inflated to cosmic scales. There is no eternal inflation, no multiverse, no measure problem. The properties of the universe are determined by the physics of the brain collision, not by random chance in an infinite landscape of possibilities. Third, and perhaps most provocatively, the cyclic model has no absolute beginning. The cycles of contraction, collision, and expansion can extend infinitely far into the past. The BGV theorem, which shows that an expanding universe must have a beginning, does not apply here because the universe is not always expanding. The average expansion rate over a full cycle can be 0, evading the theorem's assumptions. But the ekpyrotic model has its critics, and the criticisms are significant. The most serious concern is the bounce itself, the moment when the brains collide and the universe transitions from contraction to expansion. This is a moment of extremely high energy and curvature, a moment that requires a complete theory of quantum gravity to describe, and we don't have that theory yet. It's possible that, when we finally do understand the physics of the bounce, we'll find that it doesn't work as the ekpyrotic model predicts. The brains might annihilate each other. The transition might produce pathologies that destroy the smooth initial conditions the model is designed to explain. This is a genuine worry, and Steinhardt and Turok are well aware of it. More recent formulations of the cyclic model have moved away from the brain picture entirely, reformulating the essential physics in terms of ordinary four-dimensional quantum field theory without invoking extra dimensions. In these newer versions, the ekpyrotic contraction phase and the bounce are described using scalar fields in standard gravity, making the model more tractable and less dependent on the unproven framework of string theory. Whether the cyclic model will ultimately prevail over inflation, or whether both will be superseded by something entirely unexpected, remains to be seen. But it offers a genuinely different vision of cosmic history, one in which the Big Bang is not a beginning, but a recurring event in an endless cosmic cycle. In 2018, a paper appeared in the journal Physical Review Letters that proposed something altogether strange. The authors were Latham Boyle, Kieran Finn, and Neil Turok, the same Turok who had co-developed the ekpyrotic model nearly 2 decades earlier. But this new idea was completely different. It didn't involve brains or extra dimensions or string theory. It involved something far more fundamental: symmetry. The symmetry in question is called CPT symmetry. This is one of the deepest and most robust symmetries in all of physics. It states that the laws of physics remain unchanged if you simultaneously perform 3 transformations. You replace every particle with its antiparticle. That's the C for charge conjugation. You reflect space like a mirror. That's the P for parity. And you reverse the direction of time. That's the T for time reversal. Individually, each of these symmetries can be violated. Nature does distinguish between left and right in certain particle interactions. Nature does distinguish between matter and antimatter, and nature certainly seems to distinguish between past and future. But the combination of all 3, CPT, is believed to be an exact symmetry of nature, never violated by any known physical process. This is not a symmetry we imposed on nature. It is a symmetry that nature imposed on us in the 1950s. Physicists Wolfgang Pauli and Gerhard Lüders proved mathematically that any quantum field theory that respects a handful of very basic principles, things like locality, the idea that interactions happen at specific points in space, and Lorentz invariance, the idea that the laws of physics are the same for all observers in uniform motion, must automatically possess CPT symmetry. It's not an optional feature. It's a theorem, a logical necessity. If the basic framework of quantum field theory is correct, then CPT symmetry must hold. And decades of experiments probing every crack and corner of particle physics have confirmed it without exception. Now, think about what that means for the Big Bang. The Big Bang is a moment of extraordinary asymmetry in the standard picture. Before the Big Bang, there's nothing. After the Big Bang, there's a universe full of matter expanding through time in a particular direction. The Big Bang seems to break every symmetry imaginable. It's a point where matter appears from nothing, where time suddenly acquires a direction, where space springs into existence. Boyle, Finn, and Turok proposed that this symmetry applies not just to the laws of physics, but to the entire universe. In their picture, the universe does not spontaneously violate CPT symmetry. Instead, the universe after the Big Bang is the CPT mirror image of the universe before the Big Bang. If you could somehow look backward through the Big Bang to the other side, you would see a universe that is the exact reflection of our own. Where our universe is made of matter, the mirror universe is made of antimatter. Where our universe extends forward in time, the mirror universe extends backward. Where our universe has a particular spatial arrangement, the mirror universe has the opposite. The two universes, the universe and the anti-universe, emerge together from the Big Bang, extending in opposite directions through time like the two halves of an hourglass. In this picture, the Big Bang is not a beginning. It is a point of maximum symmetry, a boundary between two mirror image halves of a larger CPT symmetric whole. The philosophical implications of this are dizzying. In the anti-universe, from the perspective of someone who lived there, time would flow forward just as it does for us. But their forward would be our backward. They would see their universe expanding away from the Big Bang, just as we see ours expanding away from it. They would feel the arrow of time pointing away from the Big Bang, just as we do. Both halves of the hourglass would be equally real, equally valid, equally convinced that they were the real universe, and that time flowed in the correct direction. The Big Bang would be a two-sided mirror, and neither side would be able to look through it to see the other. This idea, elegant as it sounds, has some powerful consequences. First, it naturally explains the arrow of time. In both halves of the universe, entropy increases away from the Big Bang. But in the anti-universe, away from the Big Bang means backward in time. So, from the perspective of someone living in the anti-universe, if such a person could exist, time would appear to flow in the opposite direction from ours. The arrow of time in the CPT picture isn't a fundamental feature of the laws of physics. It's a consequence of the universe's global symmetry. Second, the CPT symmetric model makes a striking prediction about dark matter. In the standard model of particle physics, there are 3 types of neutrinos, all of which are left-handed. They spin in one direction relative to their motion. But many theoretical models predict the existence of right-handed neutrinos, which would be extremely massive and interact with ordinary matter only through gravity. In the CPT symmetric universe, the requirement of CPT symmetry naturally produces large numbers of these heavy right-handed neutrinos, and one of them would be stable. Boyle and Turok calculated that if this particle has a mass of about 480 million times the mass of a proton, It would account for exactly the observed amount of dark matter in the universe. This is a specific, testable prediction. If it turns out that dark matter is indeed made of heavy right-handed neutrinos with this particular mass, it would be powerful evidence for the CPT symmetric model. Future experiments, including galaxy surveys from the Euclid satellite and the Vera C. Rubin Observatory, may be able to test this prediction by studying how dark matter clumps on different scales. Third, the model predicts that one of the three ordinary neutrinos is exactly massless, a prediction that can be tested by experiments measuring neutrino masses. And fourth, it predicts no primordial gravitational waves from the early universe, which distinguishes it from most inflationary models that predict a detectable gravitational wave background. The CPT symmetric universe is still a work in progress. Boyle and Turok have acknowledged that their model does not yet explain the observed fluctuations in the cosmic microwave background as completely as inflation does. They have proposed mechanisms for generating the fluctuations, but these mechanisms require further development and testing. The model has also sparked debate about its mathematical consistency and its relationship to other approaches in quantum cosmology. But the core idea that our universe has a mirror twin on the other side of the Big Bang, extending backward through time, made of antimatter, is hauntingly beautiful. It suggests that the Big Bang isn't a wall at the beginning of time, but a mirror at the center of a much larger structure. And what looks like the beginning is really just the middle. There is yet another approach to the question of what came before the Big Bang, one that comes not from quantum gravity or cosmology, but from the very heart of string theory itself. Gabriele Veneziano, an Italian physicist working at CERN, is widely considered the father of string theory. In 1968, while working as a young researcher at the European Organization for Nuclear Research in Geneva, he wrote down a mathematical formula that described the interactions of strongly interacting particles. He wasn't trying to invent a new theory of everything. He was simply trying to find a mathematical function that matched the observed patterns of particle collisions, the way certain particles scattered off each other at various energies and angles. The formula he found, known today as the Veneziano amplitude, was elegant and surprisingly powerful. But he didn't know it at the time. What he had written down was secretly describing the vibrations of tiny, one-dimensional objects, strings. That realization, which emerged over the following years through the work of Yoichiro Nambu, Holger Bech-Nielsen, and Leonard Susskind, launched the entire field of string theory, one of the most ambitious intellectual enterprises in the history of science. String theory proposes that the most fundamental constituents of the universe are not point-like particles, but tiny, vibrating strings of energy, so small that they operate at the Planck scale, far beyond the reach of any conceivable microscope or particle accelerator. Different modes of vibration correspond to different particles. One mode gives you an electron, another gives you a quark, another gives you a photon. The incredible diversity of particles we observe in nature is, in the string theory picture, just the many different notes that a single type of string can play. It is a beautiful idea, and while it remains unproven, it has generated a wealth of mathematical insights that have influenced virtually every branch of theoretical physics. Decades later, In the early 1990s, Veneziano turned his attention to cosmology, and he realized that string theory had something profound to say about the Big Bang. In standard cosmology, the Big Bang is a singularity, a point of infinite density where everything begins. But string theory has a feature that changes this picture dramatically. It's called T-duality, and it's one of the most remarkable symmetries in all of physics. T-duality states that in string theory, a universe of very small size is physically identical to a universe of very large size. If you compactify one dimension of space into a circle of radius r, string theory predicts exactly the same physics as a circle of radius 1/r in appropriate units. Very small and very large are, in a precise mathematical sense, the same. This is one of those results that sounds almost too strange to be true. But it arises naturally from the fact that strings, unlike point particles, can wrap around compact dimensions. A point particle in a circular dimension can only move around the circle. But a string can also wind around it, like a rubber band stretched around a pole. The energy associated with the particle's motion decreases as the circle gets larger, because it's easier to move in a bigger space. But the energy associated with the string's winding increases as the circle gets larger, because the string has to stretch further to wrap around it. At the critical radius where these two contributions are equal, the physics is identical whether you're making the circle bigger or smaller. The universe at radius r and the universe at radius 1/r are, as far as any physical measurement is concerned, indistinguishable. This means that the singularity at the Big Bang, where the size of the universe goes to zero, might not be a singularity at all. As the universe contracts towards zero size, T-duality suggests that it is simultaneously becoming equivalent to a universe of infinite size. The collapse doesn't end in a point. It passes through a kind of mirror, emerging on the other side as an expansion. Veneziano and his collaborator Maurizio Gasparini developed this idea into what they called the pre-Big Bang scenario. In their model, the universe existed before the Big Bang in a state that was extremely cold, extremely diffuse, and very nearly flat, expanding slowly and gently. Picture it, a vast, almost featureless expanse of space, stretching out in every direction, with matter and energy spread so thin that there are barely any interactions, barely any events, barely anything happening at all. It would be a quiet universe, a patient universe, a universe waiting, in some sense, for something to disturb its equilibrium. And something does. Due to the gravitational instability of this diffuse state, the expansion began to accelerate. But this wasn't ordinary inflation driven by an inflation field. It was a different kind of acceleration, driven by the dilaton, a fundamental field in string theory that controls the strength of all interactions. The dilaton is unique to string theory. In Einstein's general relativity, the strength of gravity is a constant, set once and for all. But in string theory, the strength of all the fundamental forces, including gravity, is determined by the value of the dilaton field, which can vary from place to place and from time to time. In the pre-Big Bang scenario, the dilaton starts out weak, corresponding to feeble interactions in the cold, diffuse initial state. As the pre-Big Bang acceleration proceeds, the dilation grows stronger, and all the forces of nature intensify. As the acceleration intensified, the curvature and the coupling strength of the universe grew until they reached the string scale, the characteristic size where stringy effects become important. At this point, string theory effects kicked in, the acceleration stopped, and the universe transitioned into the decelerating, expanding, cooling phase that we identify as the Big Bang. In the pre-Big Bang scenario, the Big Bang is not a beginning. It is a transition, a bounce from a period of increasing curvature and coupling to a period of decreasing curvature and coupling. The universe existed before the Big Bang in a very different state, and the Big Bang itself was the moment when that state transformed into the hot, dense plasma that began the standard cosmological story. The beauty of this picture is that it arises naturally from the symmetries of string theory. T-duality and time reversal symmetry, combined, predict that the universe should have a pre-Big Bang phase that is the mirror image of the post-Big Bang phase. If the universe is decelerating after the Big Bang, it was accelerating before it. If the universe is cooling after the Big Bang, it was heating up before it. The Big Bang sits at the center, a moment of maximum temperature and curvature, where the pre-Big Bang era transforms into the post-Big Bang era. But like the ecpyrotic model, the pre-Big Bang scenario faces a significant challenge: the bounce itself. The transition from the pre-Big Bang phase to the post-Big Bang phase passes through a regime of very high curvature and very strong coupling. Exactly the regime where our understanding of string theory is weakest. Veneziano and Gasparini have proposed mechanisms by which string effects and quantum corrections could smooth out the transition, but the details remain incomplete. The bounce is the Achilles heel of the model, the place where the calculations become hardest and the results most uncertain. Despite this, the pre-Big Bang scenario remains an important and influential idea. It was one of the first cosmological models to seriously engage with string theory, and it introduced concepts like the cosmological role of the dilaton and the use of T-duality in cosmology that have influenced the field for decades. And it offers yet another vision of what might have existed before the Big Bang. Not nothing, not a singularity, not a bounce from a collapsing universe, but a vast, cold, slowly expanding space that gradually heated up and collapsed inward until it erupted into the hot Big Bang we observe. So we've surveyed the landscape. We've examined the leading theories: cosmic inflation, eternal inflation, the multiverse, the big bounce of loop quantum gravity, Hawking's no-boundary proposal, and Vilenkin's quantum tunneling from nothing, Penrose's cycles of time, Steinhardt and Turok's colliding brains, Boyle and Turok's mirror anti-universe, and Veneziano's pre-Big Bang string cosmology. Each of these theories is brilliant. Each is mathematically sophisticated. Each offers a different answer to the question of what, if anything, existed before the Big Bang. And each remains unproven. But that doesn't mean they're untestable. And it doesn't mean we're stuck in the realm of pure speculation, because the universe has left us clues. Faint, subtle, maddeningly difficult to detect, but real. And a new generation of experiments is setting out to find them. The most promising source of information about the pre-Big Bang era is the cosmic microwave background. The CMB is not just a baby picture of the universe. At 380,000 years old, it is a fossil record of the very earliest moments of cosmic history, a snapshot of conditions that were set during, or even before, the Big Bang. The tiny temperature fluctuations in the CMB, the ones first detected by Kobe in 1992, carry information about the quantum fluctuations that seeded the formation of all large-scale structures in the universe, and the statistical properties of these fluctuations, their amplitude, their spectrum, their spatial distribution, their degree of non-Gaussianity. All of these properties depend on the physics of the very early universe. Different pre-Big Bang theories predict different patterns, and comparing these predictions with the data is the primary way to test them. The Planck satellite, which operated from 2009 to 2013, provided the most detailed map of the CMB ever made. Its results were broadly consistent with the simplest models of inflation, confirming the predictions of a nearly scale-invariant spectrum of fluctuations, with a slight tilt toward more power at larger scales. But the data also contained some anomalies, features that don't quite fit the simplest inflationary models. There's a hemispherical asymmetry, with slightly more power in one half of the sky than the other. There's a mysterious, cold spot in the southern sky that's larger and colder than inflation easily explains. And there's a deficit of power at the very largest scales, the longest wavelength fluctuations. Are these anomalies evidence of pre-Big Bang physics? Many physicists think so. The deficit of large-scale power, in particular, is a natural prediction of some bouncing cosmologies, where the pre-bounce contraction phase cuts off the longest wavelength fluctuations. The hemispherical asymmetry could, in some models, be a remnant of the previous eon in Penrose's CCC. And the cold spot has been variously attributed to the collision of our universe with another bubble in the multiverse, the imprint of a cosmic texture, or simply a rare statistical fluctuation. But there's another observable that could be even more powerful: gravitational waves. The inflationary model predicts that the exponential expansion of the early universe should have produced a background of primordial gravitational waves, ripples in spacetime that would leave a distinctive imprint on the polarization of the CMB. This imprint is called B-mode polarization, and detecting it has been a major goal of observational cosmology for decades. In 2014, the Bice-Petwo experiment at the South Pole announced the detection of B-mode polarization consistent with inflationary gravitational waves. The scientific world erupted with excitement. The press conference was watched by millions. Andre Lind was filmed at his doorstep learning the news, tears forming in his eyes, overwhelmed by the possibility that his life's work had been confirmed. It seemed like the question of inflation had been settled. The smoking gun had been found. But within months, the euphoria turned to ashes. A joint analysis with the Planck team showed that the signal was primarily due to dust in our own galaxy, not primordial gravitational waves, tiny grains of interstellar dust, aligned by the galactic magnetic field, emit polarized microwave radiation that can mimic the signal of primordial gravitational waves with cruel precision. The Bice-Petwo team had underestimated the contribution of this dust. The detection was retracted. It was a painful lesson in the difficulty of cosmological observation, a reminder that nature does not give up its secrets easily. Since then, increasingly sensitive experiments, BICE P3, the Keck Array, the Simons Observatory, and the upcoming CMBS-4 Stage 4 experiment, have continued to push the limits of sensitivity. The Simons Observatory, located in the Atacama Desert of Chile at an altitude of over 5,000 meters, is currently being commissioned and will feature 6 new telescopes dedicated to mapping the CMB with unprecedented precision, and CMBS-4, expected to begin observations in the late 2020s, will be the definitive next-generation experiment, deploying over 500,000 superconducting detectors across multiple telescopes in Chile and at the South Pole. Its sensitivity will be roughly 10 times better than anything that exists today. If primordial gravitational waves exist above a certain amplitude, CMBS-4 will find them. If it doesn't find them, it will rule out a vast swath of inflationary models with high confidence. Either way, it will be transformative. They haven't detected primordial gravitational waves yet, but they've placed ever tighter upper limits on their amplitude, and these limits are already ruling out some inflationary models while remaining consistent with others. Different pre-Big Bang theories make very different predictions about primordial gravitational waves. Standard inflation predicts a detectable signal. The ekpyrotic model predicts an extremely weak signal, far below current detection thresholds. The CPT symmetric model predicts no primordial gravitational waves at all, and the pre-Big Bang scenario of Veneziano predicts a gravitational wave spectrum that rises steeply at high frequencies. Unlike the nearly flat spectrum predicted by inflation, if and when primordial gravitational waves are detected or definitively shown not to exist, it will be a powerful discriminator between these competing theories. It could confirm inflation, or it could point toward one of its alternatives. Either way, it will teach us something profound about the very earliest moments of cosmic history. Beyond the CMB and gravitational waves, there are other potential probes of pre-Big Bang physics. And the diversity of these probes is part of what makes this such an exciting time in cosmology. We are not limited to a single experiment or a single type of observation. We have multiple independent windows into the earliest moments of cosmic history, and each one carries different information. Gravitational wave detectors like LIGO, Virgo, and the future LISA space mission represent one such window. LIGO and Virgo, which made their historic first detection of gravitational waves from a black hole merger in September 2015, are primarily designed to detect waves from astrophysical events, collisions of black holes and neutron stars. But the technology that makes them sensitive to these events also makes them, in principle, sensitive to certain types of primordial gravitational waves, particularly those at higher frequencies than the CMB-based experiments can probe. LISA, the Laser Interferometer Space Antenna, is an even more ambitious project. Scheduled for launch in the mid-2030s by the European Space Agency, LISA will consist of 3 spacecraft flying in a triangular formation, separated by 2.5 million kilometers, all trailing behind the Earth in its orbit around the Sun. This enormous detector will be sensitive to gravitational waves at much lower frequencies than LIGO, opening up an entirely new band of the gravitational wave spectrum. And some pre-Big Bang models, including the pre-Big Bang scenario of Veneziano, predict gravitational wave backgrounds that peak precisely in LISA's frequency range. If LISA detects a stochastic background of gravitational waves with the distinctive spectral shape predicted by string cosmology, it would be a powerful piece of evidence for the pre-Big Bang scenario. Particle physics experiments at the Large Hadron Collider and its successors represent another probe. The LHC, located beneath the Franco-Swiss border near Geneva, accelerates protons to near the speed of light and smashes them together at energies of up to 13.6 trillion electronvolts. These collisions recreate, in miniature, conditions that existed in the early universe, just fractions of a second after the Big Bang. If the CPT symmetric model is correct, and dark matter is made of heavy right-handed neutrinos, experiments at the LHC or a future collider might be able to detect indirect evidence of these particles through their subtle effects on other particle interactions. The discovery of a right-handed neutrino with a mass in the range predicted by Boyle and Turok would be an extraordinary validation of their model. And galaxy surveys from missions like Euclid and the Vera Rubin Observatory will map the large-scale structure of the universe with unprecedented precision, potentially revealing subtle imprints of pre-Big Bang physics in the distribution of matter. Euclid, launched by the European Space Agency in July 2023, is surveying roughly 1/3 of the sky, mapping the positions and shapes of billions of galaxies out to a distance of 10 billion light-years. The Vera Rubin Observatory, a ground-based telescope in Chile with an 8.4-meter mirror and the largest digital camera ever built, a 3.2 billion pixel sensor, will conduct a 10-year survey of the entire visible southern sky, cataloging tens of billions of galaxies and tracking how the large-scale structure of the universe has evolved over cosmic time. The precise pattern of how galaxies cluster, the statistical properties of the cosmic web, the distribution of dark matter on different scales. All of these carry information about the very earliest conditions of the universe, and all of them can, in principle, discriminate between competing pre-Big Bang theories. The honest truth is that we may be decades, or even centuries, away from a definitive answer. The signals we're looking for are extraordinarily faint, and the theories we're testing are extraordinarily difficult to distinguish observationally. It's possible that the ultimate answer lies beyond the reach of any experiment we can currently conceive. But it's also possible that the next generation of telescopes and detectors will uncover something unexpected, something that points clearly toward one theory and away from the others. Science has a way of surprising us like that. And there is, one more thing worth saying about all of this. These experiments are not just testing abstract theories about the pre-Big Bang era. They are testing the very nature of reality itself. Is the universe finite or infinite? Did it have a beginning, or has it existed forever? Is our universe the only one, or is it one of infinitely many? Are the laws of physics unique, or are they just one possibility in a vast landscape of alternatives? These are not merely scientific questions. They are questions about the nature of existence itself, questions that touch on the deepest philosophical and even spiritual concerns that human beings have ever grappled with, and the fact that we can address them not through pure speculation or divine revelation, but through careful measurement and mathematical reasoning. That is something worth celebrating. And so we find ourselves here, standing at the edge of the deepest question any human being has ever asked. What came before the beginning? We have theories, beautiful theories, theories that invoke the strange geometry of imaginary time, the endless branching of inflating space, the gentle bounce of quantum gravity, the fiery collision of higher dimensional membranes, the haunting symmetry of a mirror universe extending backward through time, and the mathematical elegance of strings vibrating through extra dimensions. Each of these theories is an attempt to push the boundary of knowledge beyond the Big Bang, to extend the story of the universe into a realm that, until recently, was thought to be beyond the reach of science entirely. And yet, none of them has been proven. None of them is certain. The question of what came before the Big Bang remains open, as tantalizing and as mysterious as it was when the first human looked up at the stars and wondered how it all began. But there's something deeply beautiful about the fact that we can even ask this question. That a species of primate, living on a small rocky planet orbiting an unremarkable star in an ordinary galaxy, has developed the mathematical tools and the observational technology to probe the first fractions of a second of the universe's existence, and to push beyond even that into the unknown territory that preceded it. Sean Carroll, a cosmologist at Johns Hopkins University, put it well when he said that he finds it extremely plausible that there was something before the Big Bang, but also that the Big Bang may truly have been the beginning. We're in a period of deep uncertainty, and that uncertainty is not a failure. It's the frontier. And Stephen Hawking, reflecting on the difficulty of understanding the ultimate origin, offered a characteristically wry observation that seems like a fitting note to end on. He said, paraphrasing Einstein, that not only does God play dice, but he sometimes throws them where they cannot be seen. We may never find those dice. We may never trace the full story of reality back to its ultimate source, but the search itself, the sheer audacity of asking the question and building the instruments to pursue the answer, that is, perhaps, the most magnificent thing about being human. Think about what we've accomplished. A few centuries ago, we didn't even know what the sun was. We thought the stars were fixed points of light on a celestial sphere. We had no concept of galaxies, no understanding of atoms, no inkling that space could curve or that time could dilate. And now we're arguing about what happened in the first trillionth of a trillionth of a trillionth of a second of existence. We're building telescopes to detect the faint echoes of events that occurred before the universe itself was born. We're writing equations that describe the quantum fluctuations in the structure of spacetime at scales a billion times smaller than an atomic nucleus. The distance between those 2 points, between not knowing what the sun is and debating whether the universe tunneled into existence from nothing, is staggering. And we've traveled that distance in, cosmically speaking, the blink of an eye. There will be setbacks. There will be false starts, dead ends, experiments that find nothing, theories that don't pan out. There always are. But if the history of physics teaches us anything, It's that the universe is stranger than we expect, more beautiful than we deserve, and more generous with its secrets than we have any right to hope. And if there is a moment before the Big Bang, if there truly is a before, then maybe the most important thing we can do is exactly what we've been doing for centuries: looking up, asking questions, and never, ever assuming that the story ends where our current understanding breaks down, because it never does. If you enjoyed this video, please consider hitting the like button, subscribing to the channel, and leaving a comment below to tell us what you think. Which of these theories do you find most compelling? Do you think the Big Bang was the beginning, or just a chapter in a much larger story? We'd love to hear your thoughts. Thanks for watching, and we'll see you next time.